Okay, good evening everyone. I am Siddhartha Pramanik, a PMRF scholar from Department of Mathematics, IIT Kharagpur. So this is the tutorial season for second week. So here is my website in which you can find the contact address of me. So in this season, I am supposed to solve some problems related to the content of week 2 and which does not coincide with the assignment problems. So I will write down the problems and try to explain them. Then I will solve them. So meanwhile, if you have any doubt, you can ask me by unmuting yourself or by writing in the chat box. Okay. So let me write down the keywords for the contents of the second week. So so in second week, we have saw what do mean by a subgroup of a group and some special kind of subgroup, namely the center of a group. Also, we have saw centralizer of an element. This is also in subgroup, and we have saw how to define order of an element. And we saw some special type of groups, which is known as cyclic groups. And then group homomorphisms. Okay, so I will start by solving some problem from the topic subgroups. So let me write down the problems. So let G be a group and H be a subgroup of G. Now using this H, we can construct another subgroup. So for an element small g belongs to the group G, just define the set GH G inverse as take all elements small g, small g inverse such that H comes from the subgroup H. Then so that this will also form a subgroup. So then GH G inverse is a subgroup of G. So we need to prove this. So we have taken an arbitrary element small g, and using this we have defined the set GH inverse like this. So we need to prove this is a subgroup of the group G. So let's try to prove this. So to prove a subgroup, we need to check three properties, right? So first one is closure. Second one is the identity element of the group must belong to the set. and third one is inverse of every element should belongs to that set. So let me write down as inverses. So we need to check these three properties for the set G inverse. Okay. So let's start with the first one. So we need to show that the set is closed under the group operation. So let A and B be two arbitrary elements of the set G inverse. So since they are elements of the set G inverse, so then they must be of this form GH1 G inverse, and for B GH2 G inverse for some H1 and H2 belongs to H, right? Because that is the definition of our set, that every element looks like G inverse. So now what is this product AB? This is same as GH1 G inverse and GH2 G inverse. Now if we use the associativity, then it is GH1 G inverse G. We can put the bracket here, and it is G, and it is H2 times G inverse. So this is same as GH1 identity H2 G inverse, and this is equals to GH1 H2 G inverse. So definitely this element belongs to GH G inverse, right? Because H is a subgroup, and product of two elements of H must belongs to H. So GH G inverse is closed. So first property holds here, right? So let's check the identity element belongs to the set or not. So to show the identity element belongs here, uh, we must show the identity element looks like this GH G inverse, right? For some H. So now you can see that the identity element can be written as G G inverse, and since H is a subgroup, so E must belongs to H. So this element must belongs to G inverse. That means identity element also belongs to this set. So the second property also holds. Now let's check the third one, which is inverses. So suppose A is GH inverse, an arbitrary element of the set GH inverse. So we need to prove A inverse is also lies in this set, right? So what is A inverse? So it is GH G inverse and whole inverse of this. So this is equals to, so if we break this, so then the uh, element will get the reverse order, right? Because we know that G1 G2 inverse is same as G2 inverse times G1 inverse. So if you want to see a proof of this, you can go back to the live season 1 of mine, which is there in the Excel sheet shared with you. So this one is inverse of G inverse, H inverse and G inverse. And inverse of G inverse is basically G itself. So this is same as G H inverse G inverse, right? And this definitely belong to the set GH G inverse, because H inverse belongs to H, as H is a subgroup of the group G. So this set satisfies all three properties of a subgroup, right? So hence GH inverse is a subgroup of G. Okay, I hope the proof is fine. Otherwise, you can unmute yourself and ask your doubt. Okay, now a couple of remarks about this subgroup GH inverse. So this subgroup has a name. So this is known as the conjugate subgroup of H by G. So let me write down it. This subgroup is known as conjugate subgroup of H. I hope you will see this term again and again in the upcoming lectures. So let's wait for that. And now a simple question for you. So suppose your subgroup H is abelian. So can you say this subgroup GH inverse is abelian? Just think for a moment. Okay, so the fact is H is abelian if and only if this subgroup GH inverse, this is abelian. So let me write down it. So H is abelian if and only if GH inverse is abelian, and this is true for every element small g of G. Okay, so I hope you understand the definition of abelian group. You can recall it, that every two element must commute. So this one is for you. You can try to prove this. So let me write down at exercise. And the second remark is, so what about cyclic groups? So if H is cyclic, can you say that GH inverse is cyclic? So cyclic group means it is generated by a single element, right? So here the fact is H will be cyclic if and only if this conjugate subgroup will be cyclic. And this is also true for every element G of G. So if H is generated by small h, okay, then, so let me write down as, then this is if and only if the subgroup GH inverse is generated by this element. So you just verify it. This is not a big deal. So this thing is important. That's why I put this as remark. So if you have any doubt in this, you can ask me now. Otherwise, I will move on to next problem. Okay, so let's see the next problem. So we have seen some examples of subgroups, right? But if you have some subgroup, so I want to give you a method to construct a new subgroup. So already I have given, which is the conjugate. Now I want to give you another method. So let G be a group and H1, H2 are two subgroups of G. So then using H1 and H2, we will produce another subgroup. So then so that H1 intersection H2, this is also a subgroup. Okay, I hope the question is clear. So H1 and H2 are two subgroups. So we need to prove their intersection is also a subgroup. Okay, let's see a proof for this. So again, we need to verify three properties. First one is closure. Second one is identity. And third one is inverses. So let's see one by one. So let A and B belongs to this intersection. So that means A and B both belongs to H1 and H2, right? So A and B belongs to H1 and A comma B belongs to H2. Now H1 and H2 both are subgroups, right? So the product of these elements must belong to these subgroups because they should satisfy the closure property. So since H1, H2 are subgroups of G. So this means this element belongs to both sets, right? So that element belongs to the intersection. So we have taken two arbitrary element and we have shown their product belongs to the set. So the closure property holds. Now the identity. Now we know E belongs to H1 and E belongs to H2, right? Because both are subgroups, so they should contain the identity element. So clearly E belongs to H1 intersection H2. So identity is also very clear. Now what about inverses? Inverses is also clear. So if A belongs to this intersection, that means A belongs to both H1 and A belongs to H2 as well. And since they are subgroups, their inverses belongs to H1 and also belongs to H2. So that means A inverse belongs to this intersection. So finally, inverses property also holds. So this is a subgroup. So hence H1 intersection H2 is a subgroup of G. Okay, I hope the proof is clear. So now a natural question is, instead of two subgroups, what will happen if we take finitely many subgroups? So do you have any answer? So intersection of finitely many subgroups is again a subgroup or not? Yeah, can you answer this? Anyone? Okay. So this will also be a subgroup. And the interesting fact is, we don't need finiteness. We can take any arbitrary number of subgroups. So if Hi, where I belongs to an index set capital I, is a family of subgroups, so that means it can be any finite number, infinite number, indexed by any set. So then their intersection, it is also a subgroup. Okay, I hope and the proof exactly follows the same way as we have done in this case for two subgroups. So I'm not going to write down the proof again. So we have taken intersection. So now if I ask you, what about union of two subgroups? So what will happen if we take H1 union H2? Is it a subgroup? Do you have any answer? Just think for a moment. May not be a subgroup. Okay. So do you have any example for that? Sorry, can you speak little louder? Yeah, that is correct. So let me put that as second remark. So the union may not be a subgroup. It can be sometime, but not always. So it may not be a subgroup of G. So as he says the example, let me write down the same example. So take the group G equals to R2. R2 means the set of all order pairs of real numbers, right? And the group operation is coordinate wise addition. So then it will form a group. You can check, and you can take h1 as the x-axis, which looks like this set, and h2 as the y-axis. Then you can check h1 and union h2 is not a subgroup. So this is you can just see the graph. So this is your x-axis and this is your y-axis. So if you pick an element here, let's say it is 1 comma 0, and here an element 0 comma 1, then what about the sum? Sum is the point 1 comma 1, right? So this does not lie in the x-axis or in the y-axis. So this does not belongs to the union. So it is not even closed, right? It does not form a subgroup. So you can write down the details. So let me do a very interesting problem about subgroups. So we all have heard about the group rational numbers under addition, right? So let me write down the problem. So suppose H and K are two non-trivial subgroups. I hope you can recall the term non-trivial subgroup. So trivial subgroup means is the only identity element. So non-trivial means it contains more element except the identity. Sorry, more than and also contains the identity. So two non-trivial subgroups of rational numbers under addition. So the fact is their intersection is also a non-trivial subgroup. So is a non-trivial subgroup of q comma plus. Okay. So can you prove this? Do you have any idea? Just think for a moment. Okay, let me done this. So H and K both are non-trivial, right? So they must contain some non-zero elements because the identity here is the zero element. Since H, K are non-trivial subgroups, so then they must contain some non-zero rational numbers, right? Then there exist non-zero rational numbers let's say P1 by Q1 and P2 by Q2 such that P1 by Q1 belongs to H and P2 by Q2 belongs to K, and they are rational numbers, right? So we can assume the denominators are natural numbers, where Q1 and Q2 are natural numbers. Okay, now using these two elements, I am going to produce a non-zero element in the intersection. Okay, let's see. So this is a group under addition, right? So now you can see if we add P1 by Q1, you just add it Q1 times. Then this element is equals to P1, right? So this should belongs to H because we are adding elements of H only. So similarly, if you add P2 by Q2, Q2 times, so this is again equals to P2 and this belongs to K. Okay. So we have two integers. One is P1 belongs to H and other is P2 belongs to K. Now we can assume that both these integers are positive because they are already non-zero. So uh, okay, let me write down it. Now since P1 belongs to H, so its inverse, which is minus P1, also belongs to H, and minus P2 also belongs to K, right? So so you have P1 and minus P1 both belongs to H. So one of them should be positive, right? Either P1 is positive or minus P1 is positive. So similarly for P2 also. So we can assume P1 and P2 both are positive. So without loss of generality, we can assume P1 and P2 both are positive means they are natural numbers. Okay. So now, so what is this integer? P1 times P2. So this is same as adding P1 P2 times, and this is same as adding P2 P1 times. So this element, so this element must belongs to H because P1 is an element of H, and this element must belongs to K. But these are same elements, which is P1 times P2, right? So this element P1 times P2 must belong to the intersection, and this is a non-zero element. So H intersection K is a non-trivial subgroup. Okay, is the proof clear? If you have doubt, you can ask me. Okay, just think for a few seconds. Okay, now let's do one more problem about subgroups. So I guess this is problem number 4. So we all know about the group GL2R, right? Because it was introduced in first week itself, I think. So the question is, you need to found which of the following are subgroups of GL2R. So which of the following are subgroups of GL2R? Okay, let me write down the sets one by one. So first one is say H equals to A belongs to GL2R such that determinant of A is greater or equals to 1. Second one is A belongs to GL2R such that determinant of A is equals to e power some A. So where A is some real number. Okay, I hope it is clear, the description of this set. And the third one is A belongs to GL2R such that determinant of A equals to 2 power n for some non-negative integer n. And the fourth one is A belongs to GL2R such that determinant of A is a rational number. So just let me write determinant of A belongs to Q. Okay, so can you tell me which of the following are subgroups and which are not? Just think for a bit. First one is obviously a subgroup. Yeah, it is not a subgroup. Yeah, correct. What about the second one is a subgroup? Yes, correct. Yes, correct. What about fourth one? Yeah. So the answer is yeah, you are correct. It will be a subgroup. So first one is not a subgroup. Okay, let me write down the here. Second one will be a subgroup. Third one is definitely not. Fourth one is a subgroup. Okay, let me write down a quick justification for this. So for first one, all these matrices in this set should uh, should have determinant greater or equals to 1, right? So if we take the matrix, this diagonal matrix 2 0 0 1, then its determinant is 2. So determinant of A equals to 2. So this implies A belongs to H. Now what about A inverse? Now A inverse is 1 by 2 0 1, and this does not belongs to H because its determinant is 1 by 2. So it is not satisfying the inverse property, which is every element should have inverse in this set. So first one is not a subgroup. Second one is a subgroup. All three properties will hold. Let me quickly write down this. So if A B belongs to H, that will imply determinant of A is e power A, and determinant of B is e power B for some real numbers AB. So what about the determinant of the product? So determinant of the product is just the product of the determinants. So it is e power A times e power B, which is e power A plus B. So that means AB belongs to H. And the identity element, so what is the determinant of identity element? It is 1. So we can write it as e power 0. So identity element also belongs to H. And for uh, data equals to e power A, we know data of A inverse, which is just 1 by determinant of A. So it is 1 by e power A, e power minus A. So this will imply A inverse belongs to H. So all three properties are holding. So B is a subgroup. Now for the third one, uh, you can see the inverse property will not hold. So again the same example will hold here. So let's take H equals to 2 0 0 1. This will belongs to H, but this element does not belongs to H. So C is not a subgroup and D is a subgroup. So okay, let me write down. So if A and B belongs to H, this implies their determinants are rational numbers. So product is also a rational number because product of two rational number is rational number. So it belongs to Q. So the product is in H. Now definitely the identity element belongs to H because determinant is 1 here. And if A belongs to H, so that will imply determinant of A belongs to the rational numbers. In fact, it is non-zero rational number, right? Because we are in GL2R. So determinants are always non-zero. So this imply 1 by determinant of A is also rational number. So determinant of A inverse is a rational number. So that will imply A inverse belongs to H. Okay, I hope the proof is clear. So two of them are subgroups and two of them are not subgroups. So let me ask you one more question here. So in C, instead of non-negative integer, if we take any power, any real number, then what will happen? Or let's say just an integer. Yeah, if we take all integers, then it will be subgroup. So you can check that. Okay, let me do one more interesting problem about subgroups. I think this is 5. So let H be a proper subgroup. Proper subgroup of Z. So proper subgroup means it is not equals to the whole group. Z means Z under addition, obviously. And also assume these three elements 18, 30 and 40 are in H. So the question is you have to determine the subgroup H. So as you have seen, every subgroup of Z is of this form n comma Z, right? For some n greater equals to J. So H is also of the form n comma Z. So you need to find out this n. So just think for a minute. Uh, can you repeat once? I think. Sorry. You can write down in the chat box also if you want. Yeah, the answer is correct. So how to do this? So let me write down a quick justification. So you can see 18 belongs to H, right? So that will imply 18 plus 18, 36 belongs to H. So that will imply its inverse, which is minus 36, is also in H. So uh, 30 and minus 36 belongs to H. So their sum, which is equals to minus 6, it should be in H. Again, uh, minus 36 comma 40 is in H, so their sum should be in H, and this is 4 belongs to H. So minus 6 and 4 belongs to H. So again, so their sum should belongs to H, and which is minus 2 belongs to H. So that will imply its negative, which is 2 itself belongs to H. So this implies H contains the subgroup generated by 2, which is 2Z, but why it is equals to 2Z? Can you say? So uh, no, I'm saying H contains all multiples of 2. That is okay. But why H is exactly equals to 2Z? So why it should not contain any other element of Z? Look, in the question, we have mentioned H is a proper subgroup. Okay. So if H contains some odd number, let's say 2n plus 1. So then we know 2n is already in H. So 2n plus 1 minus 2n. So 1 belongs to H. And if 1 belongs to H, that will imply uh, whole Z is subset of H. So that will imply Z is equals to H. This is a contradiction, right? Because we have taken H is a proper subset. So H must be equals to 2Z. So did you get the point? Okay. So let's back to the first page. So I have done some problems related to subgroups. So let me start with some problems related to order of an element. Yes, you can ask, but not from the assignments. Okay, okay, yes. Uh, you want to say how the subgroups of this group looks like. So So wait, if H is a subgroup of G, then H, okay, what is K here? No, no, what is K? K is equal to, okay, K union minus K, where K is H intersection 0, comma, yeah, yeah, actually I have to think about it. So what you can do is you can post it in the discussion forum. So we all TAs are active there, and I hope I will get back to you. Or maybe if someone else can answer, you can answer. So you put it in the discussion forum, okay? So that we may not forget. Okay. So what we are doing is some problems related to order of an element. Okay. So let me list down some properties of order of an element, which will help you to do the assignment problems and which is important for you. And this is important to understand the concept of group and whatever you have learned in these 2 weeks. Okay, let me write down one by one. So assume G is a group, and let's take an element, sorry, two elements, small g and small h belongs to G. So first property says if order of G is n, let's say it is finite, then G, G square, G power n, these all are distinct elements of G. Okay, and from this we can conclude that the order of the element G must be less than equals to the order of the group, which is the cardinality of the set G. So let me write down the second one. So order of G is always equals to its order of the inverse. It may be infinite, may be finite, but in both cases they should be equal. The third one is order of the element H is same as order of the element GH G inverse. Remember, GH G inverse is a conjugate of H. So conjugate elements has same order. Okay, let me write down the fourth one. So if order of G is n and it is finite, and G power m is equals to identity, so then n must divide m. So this is one useful fact. And fourth one is basically a formula. So if order of G equals to n, then order of G power n, and we can describe this. This is same as n by GCD of n comma m. So let me prove one by one all these formulas. So first one is, if order of G is n, then these n elements all are distinct. So given is order of G is n and which is finite. So what will happen if any two element, means sorry, some two element in these n elements are equal? So if G power I equals to G power J for some, let's say I, so you can see, then we can write it as G power I times G power I inverse and G power J G power I inverse. And G power I inverse is basically, so this will give me the identity element. And what about this? This is G power J times G power minus I. So this is G power J minus I. Now you can see uh, I less than J less equals to A. So if we subtract I here, so J minus I is less equals to N minus I, and it is strictly less than N. But order of G is N. So N is the smallest positive integer such that G power N equals to identity. So this should be a contradiction, right? Because order of G is N. So this cannot be true. So hence G, G square up to G power N, and this is equals to identity. These all are distinct elements. Okay, so I hope the first one is clear. So these all are distinct elements of G. So G contains at least n element, right? So order of G must be greater equals to n. So G contains at least n elements. So this means order of G is greater equals to n, and this is same as order of G. So the first one is clear. So all are distinct elements and this relation holds. Okay, let me do the second one, which is order of G is always equals to order of G inverse. So I will break down it in two cases. First one is when order of G is finite, and other case is when order of G is infinite. So let's do the infinite case first. So case 1, order of G is infinite. Now if order of G inverse is finite, so that will imply G inverse power n equals to identity, right? But this is G power minus n equals to identity. So if we multiply G power n both sides, so we will get G power n equals to identity, and n is a finite number. So this cannot be true because order of G is infinite. So this is an contradiction. So order of G inverse cannot be finite. So it must be infinite. So in case 1 we have proved. Now case 2. So here assume order of G is finite and it is equals to n. So we need to prove order of G inverse is equals to n, right? So that means n is the least positive integer such that G inverse power n should equals to identity. Here we can write G power n equals to identity. So from this we can say G power n inverse should be equals to inverse of the identity. So that means G power minus s minus n equals to identity. So from this we can conclude order of G inverse should be less equals to n, right? Now we need to prove it is exactly equals to n. So what will happen if it is less than n? So if order of G inverse equals to m, which is strictly less than n, that will imply G inverse power m equals to identity. So that will imply G power minus m equals to identity. So again we will multiply G power m both sides. So this will imply G power m is identity. But order of G is n. So n is the least positive integer such that G power n is identity. And m is less than n. So this is not true. This cannot be true. So this is a contradiction. Hence, order of G inverse, it must be equals to n. Is it clear? Okay, so let's move on to the next property. So second one is also done. Third one is order of H is same as order of GH G inverse. And this proof is also same as the second one. So I am not going to do that. So you can try to prove this on your own. Or if you have doubt, you can post in the discussion forum. So let me do the fourth one. So order of G is n and G power m is identity. So then n must divides m. Let's do this. So what is given? Order of G is equals to n, which is finite, and G power m is identity. And what we need to prove? We need to prove n divides m. Whenever you trying to prove something, so always first remember what is given and what you need to prove, and then try to link those two things. Because here in group theory, almost many things come naturally. So we need to prove m is divisible by n. So if m is 0, then 0 is divisible by every non-zero integer, right? So n divides m. So let m is non-zero. So now if we apply the division algorithm, so I hope all of you know the division algorithm. Now by division algorithm, so we want to divide m by n. M equals to n times some q plus r, right? Where q is the quotient and r is the remainder. So if we divide m by n, q will be a quotient and r will be remainder. So where uh, either r is 0 or r should be less than n and it should be greater than 0, right? So if we can prove that r is 0, then m equals to nq, and then n will divide m. So we want to prove r equals to 0. So now uh, r is equals to m minus nq. So what is g power r? G power r is g power m minus nq, and this is same as g power m times g power let's say minus nq. This is same as g power m, and this is same as g inverse power n times q. So these both are identity elements, right? So this is also identity and this is also identity. So the product is identity. So we are getting g power r is identity. But we have seen that order of g is n. So n is the least positive integer such that g power n is identity. So r cannot be less than n and greater than 0. So this means r has to be 0. And that will imply m equals to nq. That means n divides m. I hope this proof is also clear. So this needs little bit number theory. So I have just used the division algorithm. I hope you know this. So we have done the fourth one. Order of G is n and G power m is identity. So n must divide m. And the fifth one, the formula. This one is very important to calculate the order of powers. So okay, let me write this as finite. So if order of G is n finite, then order of G power n must be n by GCD of n comma n. So let's do this. So fifth one. So what is given is order of G equals to n, which is finite. We need to find order of G power m. Means we need to prove it is equals to n by GCD of n comma n. So let GCD of n comma n equals to d. So that then d divides n as well as d divides m, right? So we can write n equals to some n1 times d and m equals to some m2 times d, right? And this, sorry, m, we can take m1 times d. And we can assume this n1 and m1 has GCD 1. So this is from number theory, you can go back and look. So what we need to prove? Order of G is equals to n by d. So that is equals to n1, right? So so we need to prove this is equals to n1. So now G power m, let's take its n1 power. So what it is? It is G power m times n1. This is same as G power, let's use this one, m1 d n1, right? But d times n1 is n. So this is same as G power m1n. So this we can write G power n power m1. But G power n is identity because order of G is n. So this is identity power m1. So this is identity. So from this we can conclude order of G power m must divide uh, n1, right? Because of the last property. Order of G is something n and G power m is identity, then n must divide. We are using this one. So G power m, order of G power m must divides n1. So now assume order of G power m is equals to an integer k. So k divides n1. One more thing. Okay. So order of G power m is k. So that means G power m power k should be identity. So this implies G power mk should be identity. So again you use the previous property. So this will imply order of G must divide mk. So that means n divides mk. Now let us substitute the value of n and m. So this will imply n1d will divide m1d times k. Now GCD of n1 and m1 is 1, this one. So we can cancel out this. So D divides, uh, okay, so I mean N1D must divides, okay, sorry, first we should cancel the D. So N1 divides M1K. Now GCD of N1 and M1 is 1. So N1 must divide K, because GCD of N1 comma M1 is equals to 1. So here we have proved this is equals to K, right? This is equals to K. So we have proved K divides N1 here, and here we have proved N1 divides K. So that means K should be equals to N1. So what is K? K is order of G power n. And what is N1? N1 is n by D, which is n by GCD of n comma n. Hence the proof is done. So I hope it is okay. So we have used little bit number theory, but this formula is very much useful. So you should remember these properties while doing problems. Okay, now let's see one interesting problem about order of the element. So this is problem number 7. Okay, so let G be a group and assume A comma B are two elements of G. Okay, and also assume order of A is 2 and B is not equals to identity. Okay, let me put a comma here. And ABA equals to B square. So then the problem is you need to determine order of the element B. So order of A is 2, B is non-identity element. They satisfies this relation ABA equals to B square. So you need to determine order of B. So you just quickly try for few seconds. So if you have any answer in your mind, you can put in the chat box or you can unmute yourself. Okay, let's do this. Now see, order of A is 2, right? Since order of A is 2, that will imply A square is equal to identity. and this will imply A equals to A inverse. So you just multiply A inverse both sides, then you will get this. So A B A, this is same as A B A inverse, right? And it is equals to B square. So what is A B square A? So we just substitute this B square here. So this is same as A B sorry okay, A B A times A. No, sorry, something is wrong here. Uh, so B square is equals to ABA. So that will imply B to the power 4 is equals to ABA square, and this is same as ABA, and we know A equals to A inverse, right? So A square is identity. So A B square A. Now here we will substitute the value of B square. So this is same as A times ABA times A. So use the associativity. This will be A square B A square. So this should be equals to B. So this implies B to the power 4 is equals to B. So this implies B to the power 3 is equals to identity. So from this what can we say? So order of B must divides 3, as we have seen in the properties. So it has only two choices, right? It is either 1 or 3. Now B is not equals to identity. So order of B cannot be equals to 1. So this implies order of B equals to 3, since B is not equals to identity. Okay, I hope it is clear. If you have doubt, you can ask me. Okay, let me go back to the keywords. So we have done subgroups, we have done order of elements, and let's do some problems of group homomorphisms. This is going to be interesting. So this is problem number 8. So I will list some functions from groups to groups. You need to check that they are group homomorphisms or not. And if they are group homomorphisms, you need to find the kernel and image. So let's write it. Check whether the following functions are group homomorphisms or not. And if they are group homomorphisms, in case of a group homomorphism, find its kernel and image. So I hope you have remembered the definition of kernel and image. So first one is f from the group r star dot non-zero real numbers under multiplication to r star dot map is f of a goes to a square. Second one is r comma plus to r plus comma dot the set of all positive real numbers under multiplication, and the map is f of a equals to mod a. Okay, number 3, f from c star dot, which is the non-zero complex numbers, to r star dot. And what is the map? F of z equals to mod z, means modulus of a complex number. And the fourth one is f from c star dot to c star dot, and the map is f of z equals to z power 3. So can you quickly check which of these are homomorphisms or not? Yes. Yeah, okay. Yeah, yes, answer is correct. Okay, let me okay, so in case of a b c, sorry, a c d, they are homomorphisms. So let me write down this. I will come back to solutions. So can you find the kernel and image in these three cases? Okay, let me prove first that these are homomorphisms. So in case of a, f of ab is ab square. So this is same as a square b square, and this is same as f of a times f of b. So first one is a homomorphism. For the second one, you can see f of 2 plus 1 is equals to uh, f of 3 equals to mod 3, and which is equals to, okay, okay, let's do minus 2 and 1. So this is f of 1 which is mod of 1 equals to 1. But f of minus 2 is equals to 2 and f of 1 equals to 1. So f of minus 2 plus 1 is not equals to f of minus 2 times f of 1. So it is not a homomorphism. So for C, what is C? C is C star dot to R star dot Z goes to mod Z. So it will be homomorphism. So f of Z1 times Z2 equals to mod Z1 times mod Z2, and this is mod Z1 times mod Z2, so f of Z1 times f of Z2. So this is a homomorphism. And third one is also similar thing. F of Z1 times Z2. This is Z1 Z2 power 3. So this is Z1 power 3 times Z2 power 3. So f of Z1 times f of Z2. So A, B, A, C, D are homomorphisms and B is not a homomorphism. So now do you have answer for kernel and image for these homomorphisms? So what about the first one? What is the kernel and what is the image? So square of a real number is always positive, right? So the image should be r plus comma dot. Let me write this. So for A, image of f is equals to f of A such that A belongs to r star dot. This is the definition. And this is equals to A square such that A belongs to r star. So you just quickly verify this is going to be the set R plus. And what is the kernel of this map? So kernel of F is a subset of the domain, right? So it is A belongs to R star such that f of A is equals to identity. So in first case the identity element is 1 because it is with respect to multiplication. So f of A should be 1. So this is equals to A belongs to R star such that A square is equals to 1. So what are the real numbers whose square is 1? So this is the set minus 1 comma 1, right? Which is two roots of unity. So what about the option C? What will be the image? So here also the image is R plus because mod Z is always going to be positive, right? So you can verify that. So let me just write down it. Image of F will be R plus. But what about the kernel? What is the kernel of this map? F of Z going to mod Z. So let's do this. So kernel of F is Z belongs to C star such that f of Z is equals to 1. But what is f of Z? So it is Z belongs to C star such that mod Z is equals to 1. So what does it mean? So set of all complex numbers whose modulus is 1. So it is basically the unit circle in the complex plane. So if I draw like this, so this is the circle, and this is sometimes denoted by S1. So this one is an important group. So the unit circle will be the kernel. So this notation is not that much standard, but you can use this by specifying. Okay. So the last one. What about this? What will be the image? Yeah, do you have any answer for this? Any guesses? Yeah, anyone? So the answer is image will be the C star itself. Okay, so let me do this. So in case of D, your F is from C star to C star, which are non-zero complex numbers. F of Z is equals to ZQ. So definitely image of F is subset of C star. So we need to prove the other way. C star dot is subset of image F, right? Then it will be equal only. So let Z belongs to C star. So Z is a non-zero complex number. So that means uh, the 1 by 3 power of Z, it also a complex number. So what will be the image of Z of 1 by 3? So this is a set, right? Set of 3 elements. So if you know little bit complex numbers, you might get. So what will be the image of Z of 1, Z power 1 by 3? This is Z power 1 by 3 whole power 3. This is Z. So this means Z belongs to the image of F. So C star is also subset of image of F. So we have proved the both way. First one is image of F is subset of C star, that is clear. And the other way, C star is subset of image of F. So they should be equal. So image of F is C star. So that means this map is surjective. Okay. So now what about the kernel of this map? Yeah, you are correct. So the kernel is Z belongs to C star such that F of Z, which is ZQ, equals to 1. So this is 3 roots of unity, right? So according to the notation of the instructor, this is G3. So third roots of unity. So later when you read about isomorphisms, you can go back to this homomorphisms and you can find some interesting properties of these homomorphisms, especially these last two. So I want you to go back in these homomorphisms when you will read isomorphisms. Okay. Okay, let's do one interesting problem about group homomorphisms. So the question is, does there exist a non-trivial group homomorphism from the group rational numbers under addition to the group integers under addition? So let's think for a few seconds if you can come up with answer. Yeah, do you have any guesses? Okay, so let's try to see what will happen when there exists a non-trivial group homomorphism. Okay, so suppose phi from q comma plus to z comma plus is a non-trivial group homomorphism. So non-trivial means, so what do you mean by trivial group homomorphism? Trivial homomorphism means all elements goes to identity, right? So non-trivial means there exists at least one element in the domain such that its image is not identity. So here uh, there exists a rational number, let's say it x, such that phi of x is not identity. So what is the identity of z comma plus? It is 0, right? So phi of x is non-zero. But phi of x is an integer, right? So let phi of x is equals to n. This is belongs to z. So n is non-zero, right? So we can write z minus 0. So now x by 2n. This is also a rational number, right? So what will be the image of these rational numbers? So we can write this. So phi of x, we can write phi of x by 2n. I mean, we can add x by 2n times. So that will give you phi of x. So this implies phi of x equals to 2n times phi of x by 2n. So this implies phi of x by 2n is equals to 1 by 2n times phi of x. But what is phi of x? It is n, right? So this is 1 by 2n times n. So this means 1 by 2. But this is not an integer. But phi of x by 2n must be an integer, right? So there is some contradiction. So I cannot be a non-trivial group homomorphism. So which is a contradiction. So that means there cannot be any non-trivial group homomorphism. Hence, there does not exist any non-trivial group homomorphism. Sorry, non-trivial group homomorphism from q comma plus to z comma plus. Okay, I hope this proof is clear. So meanwhile, if you have any doubt from the content of week 2, you can ask me. Okay, let me ask one more question about homomorphisms. So consider the function f from real numbers under addition to the group GL2R, the set of all invertible 2 by 2 matrices over real numbers, defined by f of x equals to cos x minus sin x and cos x. So check whether f is a group homomorphism or not. Okay, can you quickly check this? So you are saying it is a group homomorphism. Yeah. Uh, Not only rotation. These consist of rotation matrices as well as reflection matrices. So if you go back to the live season 1 of mine, I have proved that the set ONR which is A belongs to GLNR such that A transpose is identity. So this forms a group, and this is known as a group of all orthogonal matrices. Okay, so in case of n equals to 2, the set O2R, this will be exactly looks like this matrices. So this is one fact you can find out by yourself. So 2 by 2 orthogonal matrices has this form. So this consists of rotation matrices and reflection matrices. So that is just for another knowledge, but fact is this will be a homomorphism. So I want you to check what will be the kernel, because image is O2R, that is I have told you. So just try to find out the kernel. Yeah, any guesses? Uh, yes, all integer multiples of 2 pi. Yes. So let me write down the solution for you. So first, let's check it is a group homomorphism. So what is f of x plus y? So it is just cos of x plus y. This is minus sine of x plus y. So the fact is this is same as cos x minus sine x, and it is cos x. This times cos y minus sine y, it is sine y, it is cos y. Because if you multiply this, so what will be your first row? Let me write down one time just. So first row will be cos x cos y minus sin x sin y, right? And this is exactly cos of x plus y. So similarly, you can find out the other terms also. So let me raise it. So this is basically f of x and this is f of y. Because in right hand side, the operation is matrix multiplication, right? And left hand side we have addition of real numbers. So that is what we have proved, and this is true for all xy belongs to R. So F is a group homomorphism. So we can talk about its kernel and image. And as I have already told, the image of this map is O2R, the 2 by 2 orthogonal matrices over R. Let's write down the kernel. So kernel of F equals to x belongs to R such that f of x is a 2 by 2 identity matrix, right? So x belongs to R such that uh, cos x minus sin x sin x cos x, this matrix will be equal to the identity matrix of order 2. So that implies x belongs to R such that cos x is 1 and sin x is 0. So what are the solutions of this? So cos x is 1 if and only if we know x is equals to n pi, right? But sin n pi is not always 0. Sorry. So what are the solutions of cos x equals to 1? It is x equals to n pi. But n has to be. So let's draw the graph of cos x and try to find the solutions. So your cos x looks like something like this. So here is your pi by 2. Here your pi. Similarly, here minus pi by 2. Here pi. So this should be 2 pi. So cos x equals to 1. The solution is 2n pi. And sin 2n pi is always 0. So this set is 2n pi such that n belongs to z. Okay, I hope you have understood this. So do you have any doubt in this? So the kernel is multiple of 2 pi and image is O2R. Okay, I hope this one is fine. Okay, it's already time. So let's wrap up. So thank you all for joining this session. So you can leave now.